start the lecture. I will hand out a practice test later today because the first exam is week after spring break. Okay, the practice test will be handed out as homework 3, but it's not. You don't need to turn it in. Okay, I'm just handing it as a homework so you can actually use it as a way to study for the exam and whatnot. Okay, there's no need to write your solution and submit it or anything like that. Okay, that's number one. The second thing is now that lab 1 is done today, I will hand out lab 2 this week. For those of you who want to get started over spring break, I'll still give 2 weeks that don't include spring break to complete the lab. Okay, I always give 2 weeks. I still do that, but you will also have spring break as an extra week. So if you want to get a head start, feel free. If you are not here during spring break, you can come back and still work on the lab. So either is okay, but I am going to hand it out this week just so that you have the opportunity to start early. Okay. So those are 2 things to keep in mind. There was a homework out that is actually still due this week. Okay. Unfortunately, the lab and the homework are due in the same week because I extended the date for the lab. Okay, it was not supposed to be this way, but given the extension, they fall in the same week, but that's the way it is. Okay, so why don't we start? Okay, so let's get started. So last time I had started a new topic or new chapter from the book, which is basically classical problems in distributed systems. And we have looked at clock synchronization, several variants of clock synchronization algorithms, NTP, Christian's algorithm, Berkeley algorithm, and so on. Okay, and I also talked last time about GPS. Okay, how can you derive the position of a receiving node using landmarks, which in this case are satellite-based landmarks, and in doing so, how do you also solve the clock synchronization problem? So we did those 2 sets of techniques, and then towards the end of the class, I was talking about this notion of a logical clock, which is also called Lamport's clock. Okay, and the basic idea behind logical clocks, I have this slides from last time, was essentially to say, in many cases, we don't actually care about the actual time at which events occurred, but just the relative ordering of events, so that you can go back and say, compare events and say which event happened before which other event, but not necessarily exactly at what time they occurred. So in that case, we said we can use the notion of a logical clock, which is essentially an integer that is associated with each machine or each process, and every time an event of interest occurs, you increment the integer. Okay, and then when processes exchange messages, you piggyback the integer clock from the sending process to the receiving process or the receiving node. Okay? And in doing so, we can then actually derive a partial ordering of events. And the basic principle we are going to use there was that a message must be sent before it is received. Okay, that seems like an obvious property, but we use this very simple, intuitive idea to derive an ordering of events, okay, as we had talked about last time. Okay, so I will show you an example of that, but then we will continue from that point on and talk about today vector clocks, which is a generalization of logical clocks. I will talk about distributed snapshots and termination detection as 2 other problems, and if we find time towards the end, I'll start talking about leader detection. We probably won't get to mutual exclusion today. That will be taken care of in the next class. Okay, so just to go back to the idea of logical clocks or Lamport's clocks, as they are also called. Okay, I explained how you can timestamp events. Okay, so essentially, every process I has an integer. Every time a local event occurs, you will increment the integer by 1. Okay, so you will, within a process, you can always find an ordering of events, because if instruction I executes before instruction J, and I and J are trigger events, then essentially you'll say I happened before J, because you are going to tick the clock accordingly. Okay? Now when I sends a message to J, you will piggyback the clock value of I with the message. Okay? And then when the message is received, you will essentially take the max of the 2 logical clocks plus 1. Okay? So the receipt of the message, the timestamp that is set to the received event, is essentially the max of your local clock, max of the sender's clock, the max of those 2 values plus 1. Okay? And this is going to ensure that all the send has happened before the receive, all events before the send will essentially get ordered before all events before the receive. So it allows us to take events on two machines and order them without any clock synchronization. And here's a picture that's going to show us, okay, how this works. Okay, the two pictures show two different scenarios. This is actually not using Lamport's clocks, okay, simply incrementing logical clocks locally, but in this case you're actually using Lamport's clock to piggyback the logical clock with the message and increment it as the max of the two clock values plus one. Okay. As you can see, so this doesn't show every single event, they're just showing some random events in increasing order on process P1, P2, P3, and you will see that P1, P2 and P3 are exchanging some messages because they're part of some distributed application that requires you to do RPCs or send socket messages, any kind of message. Yeah. And essentially, because the send of a message has to happen before the receive, and due to the transitive property, all events before the send in that process would have happened before all events after the receive. Okay? Now in this case, if you do not adjust the clock, what you will see is this process's clock is advanced to 64. You send a message here, okay, and this process's clock is only at 54 at this point. Okay? So if you do not adjust the clocks, then this is going to have 54 and then 55 and so on. And now essentially the events here do not get a timestamp that are less than the the ones here. Okay? And you will see what happens in this case. Essentially, and the same is true here. You already have a event that is advanced to 60 on the local process. If you do not adjust the clock at the receive side as the max of the two, that event actually has a local clock value which is not adjusted, which is less than this. So basically it does not tell you that the send has happened before the receive. And you will see what has happened in this case is the circled events actually have been adjusted as the max of the two. Okay, so in this case it was 56. So you send 60, the local one is advanced to 56, take the max of the 2 plus 1, so this gets 61. Okay, as a result, all of these events here before the send now have a value that is less than all the events here. Okay, so that's the transitive property we wanted. Okay, and the same happens here. Okay, so you essentially send 69 here, take the max of the local clock 69 plus 1, so you get 70 there. Okay, is that clear? What logical clocks are doing. Okay. So now what this has done is the following property. Okay. If event A has happened before event B, clock value, which is the Lamport's clock value you assign to event A, is strictly less than the clock value you assign to event B. That's the property this algorithm has given us. Okay. Now that's a nice property, but it may not be the property you actually want. Okay, so I'm going to come back to this, but I'll talk about what you might actually want. So if A has happened before B, your clock value of A is less than clock value of B. Okay, but the reverse is not true. Okay, what that means is if you compare two timestamps, it doesn't tell you anything about event ordering because the implication goes in one direction. So if A happened before B, we have an algorithm that assigns timestamps such that clock timestamp or clock value assigned to A is less than the clock value of B. Okay, but just looking at two timestamps doesn't tell you anything, and the way you can see this is the following. Okay, if I just pick some random event here, 40, okay, and another event here, 90, and say, okay, I give you an event which has value 40 on process P1, value 90 on P3, what can you say about it? Okay, if you simply compare the timestamp and say 40 is less than 90, so that event has happened before the other event, that would be incorrect because you actually have to look at the message exchange. Okay, only message exchanges allow you to order events, and in this case they are actually independent events because there is no message exchange after 40 and before 90 from P2 to P3 that allows us to order those events. Okay, so some events you will actually, because the message exchanges happen, you can the clock values do indicate something, but if you take two arbitrary events and just look at the timestamp, it doesn't tell you anything. Okay? So what we are going to claim is Lamport's clock don't give us the actual property we want, which is to compare timestamp and reason about order, rather than saying given an order, assign timestamps that respect the order. Okay, so we have actually done the opposite of what we actually want. If you want to be able to compare timestamp and then definitively say just by looking at the timestamp. Okay, not if I only give timestamp, don't show this picture, can you still definitively look at them and say something about event order? So that's the property we got, and that is what the next algorithm, which is vector clock, gives us. But before I talk about that, I wanted to also give an example from the textbook, okay, which is one of totally ordered multicasting, which gives us a slightly better property than vector clocks. Okay. Vector clocks give us partial ordering of events. Okay. In particular, the picture I drew last time was the following. Okay, you have process A. Process B. Okay, that's the timeline for process A and B. That's time. And then you have a message that is sent. Okay. In that case, all the events before the send, so send and receive are two events, and all the events after the receive get ordered, because send has happened before receive, all these events have happened before the send, all these events have happened before the receive, so all the green events have happened before the red event. That's what you can actually infer based on the sending of the message. Okay, all these other events that are not marked, okay, so in this case, all the events after the send and before the receive, there is no ordering for them, because there is no message exchange to tell us anything about those events. Those for us are concurrent or independent events. Okay, we cannot derive an order. Hence, it's a partial order, not a total order. Okay. Now, if you want to still get a total ordering of events, the only way you can do this is what is called totally ordered multicast, which is after every event, after every local event, you need to actually broadcast the value of that event to all other nodes. So you are forcing a message to go out, okay, using a multicast message to go out after every local event, so that everyone else receives it, and then as a result, you can actually get a total ordering. Okay, because if every event here also triggered a message to other processes, you can derive some order, because every message is allowing us to derive some order. Okay, but there are some events that don't involve message exchange, and hence no order can be derived. So the example from the textbook is one of what is called totally ordered multicasting, which says if you want to use this scheme which gives you partial ordering and still want to derive a total ordering, the only way you can do that is to multicast your messages to every process in the system for every event, which basically allows you to get a totally ordered multicast. Okay? And then the application scenario that is actually specified, which you can use a totally ordered multicast, is essentially a replicated database. Okay? Let's say it's a bank database, but the bank has two copies of its database. So all the account information is in two separate replicas, and the replicas are in two different locations. Okay? Now, if one user makes an update to this replica, okay, another user makes an update to this replica. Let's say they withdraw some money from their account, or make a deposit to the account, or some such thing. And then later on, if you want to reason about what order this happened, because maybe they are transferring money from one account to other, and the other one is depositing some money, and you want to make sure there is enough money in the account to make the transfer, you want to be able to find a total order in this case. Okay? And the only way to do this is every query that is going to the database, which is an event, is going to be broadcast to every other replica, so that you can then say, you can get a total ordering of all the queries regardless of which database it is arriving at. Okay? Many replicated databases get around this problem by designating a master, and all queries go to the master, and the master can then order all the queries, and hence there is no problem, and the slaves simply rely on the master to tell them the event. You do not have a master, you are decentralized replicas, and you're performing updates at each of those, and you want to still reason about consistency and order of queries and whatnot, which will be important in some cases like databases. Then you have to use this technique of totally ordered multicast. And that's an example of how you can achieve it. I won't say much more about it other than for you to know that you can take Lamport's clocks, which give you partial ordering, and add multicast onto it to get a total order. Okay, so if you want to know more, you should go look at this example in more detail. I just wanted to give you a little bit of background on it. So instead, what I'm going to do now is actually focus on this property that we want, which is if you are given two timestamps A and B and you compare them, and if A is timestamp of event A is less than timestamp of event B, can we definitively say A happened before B? Okay, that's the property we want. We want, just as in real clocks, if you have synchronized clocks, you assign real timestamps, and then you compare two values. One was the file modified, when was it compiled? You can actually reason about when was the last time the source file changed and it was compiled. Okay, so by looking at timestamp, you infer something about order of events. You want the same thing here. Okay, question is, how do we take this idea and generalize? Okay, to understand that, we will introduce a property called causality. Okay, so and the definition of causality in this case is, if A has happened before B, okay, and you know that, then A is said to be causally related to B. Okay, so that's basically what we mean by causality, which means A has some causal dependence on B because A has happened before it. Maybe there's a message exchange that influences B, okay, because you know A has happened before B. Okay, and there is causality can be used in many different contexts. One example of how you can use it is to have a network that actually enforces causal delivery, which says if sending of one message M actually happened before sending of another message N, can you also ensure that the delivery also happens in that order? Okay, which means that messages, this is basically in order delivery, but not between two processes, between a set of processes. It says that if process 1 is sending a message M, process N is sending another message N, but there is a causal dependence. You know that this event has happened before that event. Can you ensure that the delivery of the first message actually happened before the delivery of the second message? Okay? So it's a generalization of in order delivery of two processes A and B that are simply using socket. Okay? So that's an example of where you can do something like this, but we will come back to that later. Right now we still need to derive a clock algorithm that will give us this property. Okay, so essentially what we want is a time stamping mechanism that says if T of A is less than T of B, A should have causally preceded. So we want the implication to go in both directions. Okay, so if A has happened before B, the timestamp should follow that ordering. If the timestamps have an order, then you should be able to infer that events also happened in that order. Okay, so let's see how to do this. I'm going to draw a picture. That's the algorithm, but I'll explain this with a picture. Okay, so let's assume there are three processes. A, B, and C. And like before, we will essentially use the notion of a logical clock, which is an integer, but in this case, rather than having a single integer value, we will have a vector or an array of integers. Okay? We will have one integer per process. So essentially, since there are three processes, okay, we'll start all, so each clock in this case is an array of three integers. Okay? So A, B, C, all of them start with 0, 0, 0. Okay? We will say, let's not call them A, B, and C, let's number them, just to be simple, call them P1, P2, and P3. Okay? So the ith element of that array is the local clock. Okay? So for P1, the first element here is its local clock value, and the other two elements are what it knows about the clock values at P2 and P3. Okay? And we'll see initially you don't know anything, so you'll just assume the clock values are 0. So as you have local events, like before, you are going to take your local clock. Okay, so this will become 1, 0, 0. This will become 2, 0, 0, so on. Okay? When P2 has local events, it will take its clock value. So basically, it's going to become 0, 1, 0, 0, 2, 0, and so on. And here, you are going to basically go 0, 0, 1, 0, 0, 2, and so on. Okay? So if you have only local events, process I will increment the ith element of its vector, okay, because that's your clock value. This is what Lamport's clock did as well. Okay. And the same thing happens like before. If you are going to send a message, okay, you are going to piggyback now the vector clock. Okay, just exactly what happened before. So if process this process is going to send a message here. Okay, let's say send 300 along with the actual message itself. Okay. Now when you receive the message, you are going to do what you did before. You are going to take the max of the two vectors. Okay. In the previous case, you took max of two integers. Now you are going to do max of two vectors, which is going to be, you are going to do max pairwise or element-wise max. So essentially, this is going to get 3, 3, 0. Okay, because you are going to increment your local value. So this would have become 0, 3, 0. Here you take 0, 3, 0, 3, 3, 0, and you take the max. So you will basically take the max of each element that gives you 3, 3, 0. Okay? And that basically process is going to continue. Okay, if this process essentially now sends a message here, okay, so this would have become 340. So 340 is going to arrive here. So this is going to increment its local clock to become 003. You take the max of this becomes 343. Okay? Yes, question.
In Lampert's clock, we took the max and added 1. Are we not adding 1 here?
You are, because you'll see that you added 1 to your local value, so that 2 has become 3 here.
So it's only it's the local one, it's not.
Yes,
That's
so increment your local value and then you take the max of the others.
Okay, so everybody, all the other nodes, we don't increment them, we just use what we were given.
Yes, indeed. So you will basically, whenever you are receiving a message, you first increment your local clock in your vector, then take the max of what your vector and the vector that has come. Okay, so that's pairwise comparison and just taking the max. Okay, so that's what the algorithm is. Okay, and now the claim that we are going to make is, if you are now given any two vectors, you can compare those vectors. Vector A is less than vector B, you can claim that A has happened before B. Okay, and we'll have to see why that is the case. Okay, the first thing is, this algorithm is going to give us the same forward property as Lampert's clock. If A has happened before B, it should be clear that we are assigning timestamp such that the timestamp of A is going to be greater or less than timestamp of B, because the same thing is happening here. We're essentially incrementing local clocks. So if A and B are local events, you are going to get an ordering automatically. When you send something, you're sending your clock, and because this gets the max of the two, it follows that the send will always have a smaller timestamp, vector timestamp than the receive event. And hence, and all of these events have a lower vector timestamp than the send. All of these events have a greater timestamp than the receive. So that property is still true. Okay. But an additional property is true, which says if I give you any two vectors here, okay, you can compare them based on what those vectors tell you. You can reason about the order of events. And the question is why and what does it tell us? You have any intuition as to why that may be the case? Okay. Let's first look at the problem we had before and see whether that problem even occurs here. Okay, so in this, I'm going to go back to Lampert's logical clock, and in this case, you could have picked any two arbitrary events. Okay, so I could have picked 40 and 90. Okay. In this case, two integers are always comparable. Okay. So 40 is less than 90, but this doesn't tell us that the event at time clock value 40 has actually happened before 90. In fact, they are independent events. Okay? So now let's take two independent events and see what happens. Okay? So in particular, I'm going to circle two events here. Okay? Let's take this event, okay, 2 to 0, and I'm going to take this other event 0 to 0. Okay? It should be clear that those two are independent because processes P1 and P2 have not exchanged any messages at all at this point in time. Okay? So now I have given you two vectors. Okay, and I ask you which vector is less than which other vector. Okay, your answer should be define vector comparison first. What does vector A less than vector B mean? Okay, then you can say I will compare this vector. So by vector comparison, we are going to say if two vectors V of I and V of J are given to you, and if you say V of I is less than V of J, it means that there should be at least one element of I that is strictly less than an element of j, and all other elements can be less than or equal to. Okay? Which means every element here has to be less than or equal to every element there. Yeah, there has to be at least one element which is strictly less than. And that's what we mean by vector comparison. So now you compare these two and say, is V of I less than V of j, or the other way around? Okay, you will say neither, because some elements here are less than the other element, others are greater. So you cannot compare these vectors fundamentally. Okay? And that is exactly what these events tell us, that these are not comparable events, they're independent events. So our vector property is actually not allowing us to derive an order of them, on them. Okay? So what vector clocks gives us is, if they're independent events, the vectors are inherently not comparable. But whenever you can actually compare the vectors and say something, you will see that those are actually related even. In particular, if I say 2, 0, 0 here, and we take another event here, and not this one now, but that one, which gives us 3, 4, 0. Okay, now I say which vector is less than which other vector, you will say this vector is strictly less than this vector. All elements here are greater. Okay? And now look at these two events. Okay, you will say this event happened before the send happened before the receive has happened before that other local event. So hence these two are comparable events, and this event has actually happened before that other event. Right? And then the vector values are telling us exactly the same thing. Is that clear? Now that's not a proof, those are just two examples as to why vector comparison actually gets around this problem. In this case, comparing two integers didn't tell us anything, but in this case, comparing two vectors actually tells us something. If they're comparable, it tells us in particular that A has actually happened before B. If they're not comparable, you say those are independent events, they don't have an ordering order. Okay, so now I will not prove it, but I'm going to give some intuition as to why we are actually able to derive this. Okay, so to understand that, inherently we need to understand what is the vector telling us. Okay, so let's take process P2, in particular, let's take this event, okay, which is marked here, and it's an event at P2. Okay. If I say this is an event 340, what does this tell us? If I just look at this. Okay. And all that we can say is it tells us the following, because this is a vector at P2, it tells us P2 has seen 4 local events. Okay, just take the clock 4 times to get there. Okay. It also says that I know something about process P1, in particular the most recent message that I received from P1 had a timestamp of 3, which is why when I took the max I saw 3 there. Okay. And it says I have not heard from P3 at all. So I know nothing about the clock at P3, that is why my local value for P3 is still showing 0. Okay. In other words, the vector clock actually at a process tells us not only what is the most current event locally, but what is the most recent event you've seen at other processes through some message exchange. Okay. And as a result, because you are now storing individual clock values that you know at other processes through this message exchanges, you can do this comparison. Because when you compare these two events, it says, what do I know about every other process in the system for each of those vectors? If you compare them, and if one is strictly greater than the other, you say that there has to be a message that was sent strictly later than the other one, which is why all my values are greater, at least greater, or at least one value is strictly greater. Okay? So that's the intuition. Okay, so the vector clocks are embedding information about what you know about other processes in the system. In particular, what's the most recent event at other processes that you know about through a message exchange. Okay, so that's the notion of a vector clock. And now you can go and think about how to prove this formally, but that is your intuition. Okay, you can prove it by contradiction. Okay, it's a straightforward proof, but I'm not going to prove it. Okay, any questions on this? So now we have what we want, which is a way to timestamp events. Okay? such that I can just look at two timestamps. Even if the actual clocks are never synchronous, I can simply look at those two timestamps and reason about event order. The events have actually causal dependence, you will get a strict ordering on the vectors. If they're independent events, you won't. It's still a partial ordering, okay, but you still get the ability to compare clock values and reason about events. Okay? Right. So, here is an example of where you can use something like this if you want to enforce causal delivery of messages, okay, which is this property. Send of a message, M happens before the send of another message. Can you actually deliver them in order? What you can do is essentially when you receive a message, you piggyback the vector clock values. You can take a look at the vector clock values and your local clock values and actually reason about what might have happened. If it looks like the message has jumped over some other message, you can see that. Because what you can see in this case is a message. So here are two messages. Okay? This is it. P0 sent a message at this time, P1 has sent a message this time. In this case, you'll see that the messages are actually multicast. This message has been sent to both processes. That message has been also sent to both processes. Okay? And what has happened is the P0's message has already reached P1 before P1 sends out its message. Okay, that's what the timeline is telling us. There's a receive event here, and then the send event has happened after this event. Okay, because that's time. Okay. Now, because of arbitrary network delay, okay, even though M has already been sent before M star, based on this ordering, you will see that P0's message arrives here, or rather P1's message actually arrives here, okay, before the first message arrives. But you can, looking at the timestamp, you can see that that first message is somewhere in transit, you haven't received it. You can buffer it and delay its delivery to the local process until that process arrives. So you see what happened here is you delayed receipt because you know there's some other message in transit based on just looking at the timestamp of 110. You can say, okay, P1 sent a message, I still haven't received it. Okay, so I'm going to wait for it because otherwise I will not enforce causal delivery. So I delay it until this message arrives and then I take delivery of it later. Okay? In this case, this can be done simply because you're multicasting all the messages, so you know there's a message that should be arriving which I have not yet seen. It's in transit somewhere, or it has been lost and needs to be retransmitted. So you can figure these things out. Okay? Yes, question?
There would be cases in the system where both VI and VJ could not be comparable.
Yes.
What do we do in that case?
Okay. So question is, there are places where VI and VJ cannot be compared. If you are sending messages, you will not see in this case you will not see that problem, okay? Because every message is actually sent to all processes. So you will basically see if there are messages in transit that you have not yet seen, but some other message that was sent afterwards has already been received. Okay? In general, you will not have this case because this is simply a multicast library that is enforcing causal delivery. Okay? In general, you can use vector clocks for any arbitrary timestamping and reasoning. And if you have two events about which you cannot reason, there's nothing you can do about it. You just say they're independent and you can arbitrarily enforce an ordering, or you can say I don't know about the ordering and I don't care about the ordering. So you can make some design decision that's appropriate to that application. That won't happen in this case because it's a multicast scenario. But in general, that might happen. Okay? Yes?
Why the local clock of process P2 do not get increased?
Repeat your question. Why does the local clock of what?
Of process P2 does not get increased.
Why does it not get increased?
Yes.
Okay. So question is, in this picture, why is the local clock not increasing? This is a network library.
Yeah.
Right? So in this case, the only events that are of interest are sending and receiving. We don't care about local events at all. So the clock values are only going to get incremented whenever there's a send event or a receive event. Okay, as I said, you basically decide what events are of interest and only then will you tick your local clock. In this case, the only values that are of interest is sending and receiving. Okay, so in this case, what has happened, just to elaborate on your question, the clock value at P2 is still 0, 0, 0. Okay? A message arrives with a clock value 110, okay, from P2 or rather P1. Okay. So this tells P2 that P1 has sent a message, that's this message, that's why it has a value of 1. But it also tells you that P1 has already received a message from P0, which is why its local clock has already advanced to 1, but you haven't seen it yet. Okay, because you know this is the first message I received, and this vector clock tells me that P1 has already received a message that is yet to be received here, because it's a multicast message. Every process needs to receive it. Right? So you can safely say, let's buffer this message, wait for the message from P0 to arrive first, because if P1 has received it before this message, this process also has to receive it, otherwise you will violate the in-order delivery property, because that you are delivering messages in the same order everywhere. Okay? So then basically you wait for that message to arrive, so then this becomes 110 and then you basically increment the clock. Okay? So that's essentially what's going on in this case. Any other questions? Yes.
But what happens when you're not enforcing multicast? So that how does P2 know? I mean, what if this scenario occurs there?
Yes, so this is a library that is actually enforcing causal communication. In our normal case, we are not enforcing causal communication at all. Messages can take arbitrary amounts of time, and one message might jump over other message, that's okay. Okay? Causal delivery is not a requirement for a typical system. Okay? Because the message propagation delays could be arbitrary. Okay? Only if you want it do you care. So that does not actually impact the overall system if you don't need that property. Okay? It might so happen that the same thing that we talked about here may actually happen where you received a message, okay? And then let's say there was a message that was sent here. A new message, and then it might so happen that you send a message here and that's received here. Okay? So essentially this message is taking much longer to propagate. So in that time P1 has already sent a message to P2, P2 has already sent a message that's been received, and this message is still propagating slowly and has been received later. That's okay so long as the ordering of messages doesn't matter. Okay? For arbitrary applications they may not matter at all. Okay? Because that's not a in-order delivery of point-to-point communication. That's a causal ordering across messages. So these kind of things happen all the time if you have TCP/IP communication. Okay? But if you need those properties for higher level consistency, you have to use libraries that guarantee you. Okay? Yes.
Same question actually. So in the P2's timeline, in the second tick when he gets the message,
Yes.
shouldn't he increase his own value and then take VC naught and do a max and set it to 101?
Okay. The question that is being asked is when you receive a message, shouldn't you take your local integer? That's the question, right? You should, but you can actually get away by not doing it either. So that I gave a simpler variant which says every time there's a local event, even when it's a receive, you should tick your local clock. Okay? This is taken directly from the book, and in the book you are basically only incrementing your clock value for local events but not send and receive. For send and receive you just do a straight max but not increase it. It still gives us that property. But I kept it more clean and simple where I said any local event, even send and receive, you increment your clock. That's not being done here, but it doesn't matter. You could have done the same thing, it will give you exactly this property. Okay? Just think of it as a small variant of what I described, but it doesn't change the actual property of the vector. Okay? But yes, if you had followed the technique I showed here, this should have actually incremented. The third tick would have not stayed 0, it would have incremented. So they are only incrementing in this example for send event, not for receive event, which is okay. Still gives us that property. Yes?
How are the coordinates assigned to the
Processes?
Like for example, in the first one it's 1, 0, 0, but in the last one it's 0, 0, 0. So how is it?
Okay, so how is the vector assigned? Is that the question? So the number of elements in the vector is equal to the number of processes in your application. Okay, so you can order the processes arbitrarily. So you see, when you start, you order them from 1 to n. Okay, and you construct a vector of n elements, and then if you are process I, then you basically are responsible for the ith element of that vector. Okay, so that's the simple thing that's being done. Any other questions on this? Yes.
So let's say we follow that example of the blue line and the red line.
Okay.
So on P1 it will be the blue line when it's the 4001, when it reaches P2 it will be 433.
Okay, so are you talking about the red?
Yes.
Okay, so here
433.
this will be 3, okay, so because there is one more here, right? So this is going to be 300, and the 400. So when you send 400, then it becomes 4. Okay.
And then when it reaches P3 it will be 43, let's say.
And this one is actually 440. Okay, because that's a send. You send 440 here. This got received here, so this becomes 443.
And then when the 300 arrives, it will be.
This is going to become 444. You just take a max. That's
So
all.
then the ordering of these events will, I mean, actually on P1 300 happened before 400, but that event, if you compare those timestamps on P3, that you don't get an ordering there. You just get an ordering of the events on P3.
Yes, so in fact when this message is received here, you can even tell that I already know a more recent event from P1 because of this transitive property, and this is a message that just arrived more slower than this other message. If you can actually tell that, but so long as you don't need causal delivery, it's okay, it doesn't actually impact it. Right? So these could just be arbitrary messages. It could say increment a counter or print something to the screen or some such thing. It doesn't matter what the message is. If you need causal delivery, you have to actually hold this message, because you will say 443, maybe there's a message in transit, etc. But we are not doing that here. Okay. So any other questions on this? Okay. So I'm going to move on to the next. So we did Lamport's clocks and we did vector clocks. These are two logical clock synchronization algorithms. What we did last time were physical clock. We actually took real clocks and synchronized. Here we are taking logical clocks and sending clock values and taking the max and trying to synchronize logical clocks, and we can reason about event ordering just based on looking at timestamp. That's the basic property we get. Okay. If you wanted actual timestamps and wanted to say what time did this event occur, this you can't use this, okay, because this is not going to tell us anything about real time. Only going to tell us about relative ordering, not absolute times at which events occur. That's the thing to keep in mind. Okay. Now with that background, we can move on to the next problem, and this problem is the what we call the problem of capturing global state. Okay. This problem occurs in a distributed system for many different cases, primarily to deal with faults. Okay, and let me explain to you what kinds of applications you can use it for before I define what is global state, and then we'll also look at an algorithm to capture global state. Okay. So let's take a simple example where maybe you have n processes communicating with one another. Okay. In fact, let's just use the example from the lab just to make it simple. You have peer-to-peer network, you have let's say pigs as peers that are communicating with one another. Okay. Let's say somewhere in the middle of the game, one pig process crashes. Okay, it just dies. Now you can say to actually ensure that you will get the results you want, somehow you have to do one of two things. Either you have to terminate all other peers and then restart everything and restart the game from the beginning. That's one approach. Okay. The second is, if you had somehow captured the state of that peer, okay, periodically, okay, and you had logged it somewhere, you can restart that peer from the most recent state, so that you can just continue from an intermediate point in the game. You don't just terminate everything and restart the game from the beginning. Okay? And this is simply called checkpointing. Okay? Every so often you save your local state, so that rather than having to do what is called rollback to the beginning and restarting the whole game, you can only restart from the most recent checkpoint and then start from there. Okay? That prevents us from losing the state altogether or wasting computations because you are rolling back all the way to the beginning. Okay? And game is just an example. This happens in many different cases. If it's a long running simulation, let's say, you start a parallel simulation and your jobs run on 10 machines, it takes 1 day to finish. Somewhere in the middle, if one process out of n crashes, then you are stuck. You have to kill all of them and restart from the beginning, unless you have periodically checkpointed your state. And then you restart you still terminate all the processes, but you restart them from an intermediate state rather than from the beginning. Okay? So that's a common technique that is used in fault tolerance. But then the question that we will want to answer is, how do you implement this checkpointing algorithm in some consistent way? Okay? And the problem basically comes up because clock synchronization may not be perfect. Okay? If you had perfectly synchronized clocks, okay, which means the clocks on all the machines where these processes run were exactly identical, you would say every hour, every process should freeze, so they all freeze at exactly the same time, and then they all write whatever their intermediate state is to disk, and then they continue. So you could say, I do hourly checkpoint, clocks are perfectly synchronized, so then if something fails, I just roll back to the most recent hourly checkpoint, so I may lose at most an hour of work. Or if you can do 1 minute checkpoint, you will lose at most a minute of work. Whatever it is, what you are assuming is that you will have a perfectly synchronized clock where everyone can freeze exactly at some time that is agreed upon. Okay? But you know, in reality, clocks cannot be perfectly synchronized. Even the best clock synchronization algorithm will have millisecond errors. Okay? So if you tell all the processes freeze at noon, what will actually happen is some might freeze 1 millisecond after noon, other might freeze few milliseconds before noon, because there's some error tolerance in our clock synchronization. Okay? So the checkpoint we get may not be exactly consistent because you are taking snapshot at slightly different points in time. Okay? Now if you restart from an intermediate state where the snapshots are not consistent, or the checkpoints are not consistent, you might have errors. Okay? Because you want to essentially restart from a consistent. When you start from the beginning, that's always consistent because nothing has happened. But when you restart from some intermediate point, you want to ensure that whatever you are doing is consistent. You don't want to start some process that's done more work and other process that's done less work or some such thing. Okay? So that basically gets us to the question of how do you capture a global checkpoint in some consistent fashion in a scenario where clocks may not be synchronized. Okay? If clocks are not synchronized, noon says freeze at noon doesn't mean anything, because you will actually stop at different times. Basically you stop when your local clock reaches noon, which has no relationship to when other processes local clock reaches noon. So you might actually now start taking checkpoints at slightly different times. Can we still ensure it is consistent somehow? Okay, because we are not going to assume any clock synchronization, because perfect clock synchronization, okay, is not available. Okay? Perfect clock synchronization is also called a global clock. Global clock means there's one clock that everyone agrees on, and your local clocks are all essentially the same as a global clock. Okay, so when you hear the term global clock, you can assume that either it's one clock everyone reads from, or your local clocks are all perfectly synchronized, so they all tell the same time. Okay? So that's the problem we have. Okay, so essentially, we want to be able to take a consistent snapshot, which is a consistent checkpoint, in a scenario where clocks are not synchronized. And if you can do that successfully, that says if some process crashes, then you can still terminate all the processes, roll back to the most recent checkpoint, okay, that you've taken somehow without help of clock synchronization, and continue from that point. Okay? Now, so that's the problem. Excuse me. So this gives rise to this issue of capturing the global state of a computation. Okay, that's what we'll call a snapshot. So global state of a distributed system will be defined as follows. So it's basically going to be the local state of each process, as well as all the messages that are in transit. Okay. The one thing I did not mention when I was saying you checkpoint state is you also have to actually checkpoint messages that are in flight. Okay. A has sent a message to B. If A only stores as memory state, okay, somehow you don't capture that there's a message somewhere in transit. It's somewhere either on the network or either on the sender side in the OS or the receiver side. That message will get lost if you restart the processes. The message. So then, if there are lost messages, you are not going to be consistent. Okay. So for a distributed system to take a consistent checkpoint, you should not only checkpoint each individual process, you also need to checkpoint all outstanding messages. Okay? And when you restart, those messages are also basically reintroduced in the system, so it looks exactly like where you left off, and nothing is lost essentially. Is that clear? How we do it is a different matter, but what you need to understand is when you have a distributed application, checkpointing is not just checkpointing the memory state or all the instructions and your memory of that process. It also looks at all the messages that are in transit, okay, which is essentially messages that have been sent but not received. Okay? Those are all messages in transit. Okay. So we'll see that you can use this. If you could do this, you'll use it for distributed recovery, or rather failure recovery, distributed deadlock detection, and so on. Okay, so now we just defined a global state. Now we are going to see how to actually capture the global state in a consistent way. Okay? And here is a picture that shows us two different checkpoints, and we'll see one is consistent, the other is not consistent. Okay, so there are two pictures here, A and B. And so we have in a distributed application 3 processes, P1, P2, P3. They are x-axis is time. You'll see there's exchanging arbitrary messages. Okay. And because we do not have a perfectly synchronized clock, if you had a perfectly synchronized clock, you would essentially stop all of these processes at exactly the same time. Okay? So at some time t, and you will checkpoint all of this. But now there's no perfectly synchronized clock, so essentially the dotted line, whenever it intersects a process, says that's the time at which that process took a checkpoint. Okay? So essentially P3 essentially took a checkpoint at this time, P2 took a checkpoint at that time, P1 took a checkpoint at this point in time, because they are not synchronized. Okay? And the question is this consistent in some way, or is there any inconsistencies in what has happened? Okay? And the claim is, in this case, the left picture actually is consistent, but the right picture is not. Okay? And then to understand that, what we need to understand is what is happening to all of the messages. Essentially, you will get what is called a consistent cut if either all messages, the send and receive of all of the messages is to the left of the cut, or both the send and receive is to the right of the cut. But if there is some message that is actually intersecting the cut, that's a message in transit. And then the send better be on the before the checkpoint, and the receive better be after the checkpoint. Okay, so in this case, this message actually you intersect this message. The send has already happened, but the receipt is going to happen later. Okay? Here is an example which tells us why this is inconsistent. So you will see what has happened in this case based on where the line intersect. The process is checkpointing at this point. It has already received M2 and processed it based on this timeline. M2 has been received, is being processed, and I checkpoint my state later. Okay. P1 on the other hand has checkpointed at this point in time. So if you restart at P1 here, it will start computing from this point on, okay, and then it will resend M2. Okay. And then if you restart P3 here, okay, P3 has already processed M2 and you are reintroducing M2 into the system, so M2 will be sent twice, okay, and get processed twice, which might result in an inconsistency. Okay, because the message was increment the integer by 1, okay, that message gets sent twice and you will increment it by 2, you are actually basically an inconsistent variable. Okay. So in this case, essentially what this is also doing is the receipt of the message has actually happened before the send as far as the cut is concerned. Okay? And you shouldn't receive messages before they are sent. Okay? Essentially by restarting this P2 here, that's what has happened. If P2 had checkpointed here or some such thing, that would not have happened, because the message would have been sent and received like you have this message. Okay? It's already been processed. It's been sent, received, is never going to be seen. Okay? In this case, this is fine. Okay, M3 is basically been sent but not received. So long as you also checkpoint this as a message in transit and reintroduce it into the system as part of restarting the entire computation, you are going to be okay. If you don't reintroduce, you have a lost message. That's not good either. You should never have messages twice or get lost. Okay, so neither of those two is good, which is why you have to checkpoint every individual process, and you also have to checkpoint messages that are in transit. In this case, M3 is a message in transit. You have to checkpoint that as well. Okay, and introduce it. Okay, so this is going to tell us what we need to have. Okay, if you get something like that, then you are going to be inconsistent because there are duplicate messages here. Okay, if you only checkpoint local state but not messages, then there will be messages like M3 will get lost. Okay, they will basically never be received because you just terminated everything. That's bad as well. Okay, so we want an algorithm that will get us a consistent cut. It will get us a checkpoint of every single process, and we will also checkpoint the socket buffers. Okay, messages in transit are essentially TCP/IP socket buffers. These are messages that have been either sent or received. They are in OS buffers but not been delivered. We're clear what we want. Now we'll talk about the algorithm. Any questions on this? The notion of global state, or what is a consistent cut or a consistent global checkpoint versus not consistent global checkpoint.
What is the use of storing the in-flight messages?
What's the use of storing the in-flight messages, or why you want to store the
Why
in-flight
do you want to
messages?
store it?
So that's a good question. The question is, why should we store in-flight messages? Okay, so let's take the same example. Okay, let's assume that you have taken a checkpoint where process P3 has stored its state at this point in time, P2 has stored its state at that point in time, P1 has stored its state at that point in time. And let's say one of these processes crashes. Can you say, okay, I will terminate all processes, and I'm going to start P1 from this point on, because that's the most recent checkpoint. I'll start P2 from this point on, and I'll start P3 from this point on. And they'll just start computing from this point. Okay, in that case, what do you think will happen? Okay, because P1 is starting here, okay, M3 it are already set, so it will just continue executing. It's not going to resend M3. Okay, okay, P2 is getting starting from here. But now, because you did not checkpoint messages in transit, M3 will never be received and processed by P3. Whereas if there was no failure, this message would eventually have been received at this point, okay, and you would have processed it. So as now you have a message that has been sent by P1 that will not get resent after restart, but it will never be received by P2 either. Okay, so now you have a lost message, and that was message had some information in it, P2 will never receive it. So again, if that message was increment this variable, okay? So if you restart at this point without reintroducing M3, your message, that variable will be off by 1. Okay, so that introduces an incorrectness in the system. In this case also you have a problem, okay, because M2 in this case is sent twice, so you have duplicated the message. Again, it will change the state in a way that will be inconsistent. Okay? And the increment of variable is a trivial message. It could have been a database query that was sent over the network. Okay? You will never perform that operation.
If operations are idempotent, then even this cut will be consistent cut.
If operations are idempotent, which means an idempotent operation is one where redoing the operation does not change the state. Okay, if every operation is idempotent, then you will essentially have a consistent cut in that case. That's not a problem. Okay, you cannot have lost messages, but you duplicate messages don't cause problem. But typical process applications are not written for idempotency. Right? I mean, if you have a database and you say deposit $100 into somebody's account, if I send another query saying deposit $100, you will get $200 in that case. You will be richer than you should be. In this case, you may lose money because some query got lost and the money never got deposited. Okay, these are processes in a bank database. Yes.
So, like just to clarify, so first the cut is a little wavy because like when all processes know that they have to pause at say T0, because the unsynchronized it's a bit like upside in here, upside in there, so that's why it's wavy.
Right. The question is, why is this cut funny looking like this? They seem to be halting at different points in time to take the cut rather than at the same time, and as you rightly pointed out, clocks are not synchronized. So you're still telling everyone take a snapshot at noon. Okay? But noon here occurs slightly at different points in time because your clocks are not, they're off by maybe a few seconds here or there. So
yeah, so in that figure where P3 is pausing you said that it would have received M2, but that's not true because when P3 pauses, at that time P2's, just if you follow the curve to P2, M2 is not being sent. So how do you say that when P3 pauses, it received M2?
Okay. The question that is being asked is for the second figure, I claim that M2 has already been received. Okay?
Yeah.
And you are saying, how can we claim M2 was received? Is that your question?
Yeah.
Okay. So you have to distinguish between two things. You have to distinguish between normal processing and restarting the computation. This is simply normal processing. In this case, nothing has failed. Okay. So all that has happened is you took a snapshot at this time. Okay. And P2 kept computing. Okay. And as it computed, it basically sent M2 and it got received here. Okay. And simply because the clocks are not synchronized, it just so happened that P3 took a snapshot here. Okay. So essentially when it took a snapshot here, it has already received and processed M2. That is what has essentially happened. Now the problem is if you take that snapshot and if you terminate all the processes and restart them, then everyone is basically starting from their checkpoint periods. So what will happen is your P2 is restarting, but is restarting from this point in time. So it will compute forward and send M2 again. Okay? And since P3 is restarting from this point, it's processed, it will get a duplicate message and process. That's the problem. Okay, so you have to distinguish between normal operation and what happens after restart. Any other questions here? Okay, so we will now talk about distributed snapshot algorithm. It's actually a very simple technique. Yeah, and I'm going to show you how do you do this using any simple TCP/IP channel. But before I even present the technique, you can think about what you are trying to achieve. Okay, so why is this called a distributed snapshot? What's the intuition you want? So the best analogy is to think about a photographer that, let's say, is taking a picture of the sky. Okay? Let's assume that you're a photographer, you're taking a picture of the sky. Let's say the sky has some birds that are flying around. Okay? Let's also assume that your camera's field of view is not big enough to capture the entire sky in one picture. Okay? So what you will do is you will take a picture maybe of the left part of the sky, the middle part of the sky, the right part of the sky, and then you can just lay them and paste them together and you will get a picture of the sky as it was when you took that picture. Yeah, and you want to claim that if you want to take a consistent picture of what the sky looked like when you took these pictures, then you want one of two properties. You want two properties. Okay? Since there are birds flying around and you don't control how they fly, you want to ensure that the pictures, all three pictures together has captured all the birds that were in the sky. Okay? So you don't want any missing bird. Neither do you want a duplicate bird. So if you took a picture here, okay, and then if that bird actually flew to the middle and you took a picture again, that you photographed that bird twice. That's a duplicate message. Okay? Or vice versa, you took a picture here and there's some bird in the middle of the sky that flew to this part of the sky. You took a picture here, then you are not taking a picture of that bird at all. That's a missing message. Okay? So essentially, you are taking this snapshot at slightly different times, and because the state of the sky is changing, in order to say it's consistent, okay, I have to ensure that every bird that was in the sky is actually captured exactly once in some picture. Neither is it missing from all pictures, nor is it photographed. Okay? You want exactly that property here, where you will have messages in transit. Okay? You would have done a socket send, or you would have basically started an RPC message. So there are some messages in transit. So you want to ensure that all of these messages are also logged, and if there are messages in transit, they are logged exactly once. You don't miss them, neither do you log them twice and then reintroduce them. Okay? So that's the analogy we are going to actually use in this case. Okay, is that clear? What we want now, let me show you using another picture how to do this. There are more pictures here, but they are a little confusing. Okay, these are pictures from the book, but I'm going to show you the algorithm has a simple set of message exchanges. So let's take some processes that are part of a distributed system. So process A, process B, process C, process D. And let's say they're communicating using simple TCP/IP sockets. Okay, and as you know, sockets are bidirectional. You can send and receive messages on any socket. Okay. So which is why I've shown two arrows. Okay, one is the forward channel for the socket, the one is the reverse channel for it. And these processes are simply exchanging normal messages, doing some distributed computation. What it is, we don't care. Okay. So if you want to now take a consistent distributed snapshot, here is how your algorithm is going to work. We'll say any process can initiate a checkpoint, saying it's time to take a checkpoint. Okay. And the way you will do this is when your process initiates a checkpoint, it essentially writes its memory state to disk. Okay, so you essentially take all your memory contents and you just write it out to disk. Okay, that's now the local state of that process has been written to disk. Everything that you have in memory is now actually you saved a copy in disk. But you also need to capture messages in transit, and you need to tell other processes to also store their states on disk. So the way you are going to do this is you are going to send out a special message called a marker message on all your outgoing channels. Okay, in this case, A has two socket connections, one to B and one to C. So you send a marker message. Marker message is a special message saying take a checkpoint. Okay. So this marker message is now going to propagate along with other messages, and let's say it hits B. Okay. As soon as B receives a marker message, it does the same thing recursively. It stores a copy of its memory contents on disk, and it sends a marker message on all its outgoing channels. Okay. So essentially you will send a marker message here, M, that starts going out. Okay. The only connection it has to is to A, so it's going to simply send a marker message in the reverse direction. Okay. And what you do as soon as you receive the first marker message, okay, is you not only take a snapshot and send a marker message on all your outgoing channels, but you also start saving a copy of all your incoming messages to disk, because those are messages in transit. Okay. So when A sent out a marker message out on to B and C, it was also on the incoming channels, it is now taking all of the messages that are coming in the socket and storing a copy of them. Okay. So let's say I'm going to use a different color. So we are going to call these red messages. Okay, so same thing is going to happen with C. A initiated the checkpoint, sent a marker message to C. In the meantime, C is sending normal messages, which are red messages, out to A. Okay, when C receives this marker message, it is going to store a copy of its memory state onto disk, and it's going to send a marker message out on the outgoing channels. Okay, and it's going to start recording its incoming channels, which is in this case you have a channel from D. Okay, so essentially you start recording on your incoming channel until you receive a marker message. You know that if you send a marker message to some other process, another marker message is going to come back on your incoming channel, because once that is received, it will send a message on its outgoing channels. Someone else's outgoing channel is your incoming channel. Okay, so you will always receive a marker message. So essentially, your outgoing marker message says start recording socket messages. Incoming marker message says stop recording. Okay, so as any process can start a snapshot, and the way you do this is you checkpoint your local state. You send marker messages on your outgoing channels, which say start recording to the other one, and you also start recording your incoming channels. Those will go to your neighbors. They will then send you marker channels as well as to anyone else they are connected to. Until then, so basically this goes here, and until this marker message comes back from C, all the messages that were sent prior to that get stored. Okay? We assume that these are in order channels, that you basically don't get out of order delivery. TCP/IP gives us that property by definition. All TCP sockets are in order. If you send two messages, two sends on socket, they are actually delivered in that order. Okay, so you will never have the case where this marker message was actually is going to jump over and get delivered before. That won't happen in this case. So basically you will now capture the local state of every process, and you will save all the messages in transit. Okay, those are all messages that have been essentially sent by your neighboring process before it took the checkpoint. Yes, because after it takes a checkpoint, it will not resend those messages. You have already taken your checkpoint. So these are all messages in flight that will basically arrive after you have taken the checkpoint. So you must store them, okay, because the other entity is not going to resend them. Okay, so those are essentially all the messages in transit. Okay. So it's a very simple algorithm. Okay. You essentially, any process can start this checkpointing distributed snapshot algorithm. And the way you do this, you save your local state, you send markers on your outgoing messages, you start recording your incoming messages, you keep recording until you get a marker on your incoming message. Anytime any process receives a checkpoint, it will do the same thing. It will start immediately. If this is the first checkpoint, it will save its state. It will start sending messages, marker messages go on the outgoing, start recording the incoming until you get markers in it. Okay? Any questions on this? Yes.
So if each A and B are, say, like running two threads, and they have, so there are two connections between A and B,
Right.
is each of those threads responsible for saving both its local state and all of the global state?
Okay, that's a good question. So, if you have multi-threaded processes and you have multiple socket connection between processes, what do you do? Okay. So, as far as the local state is concerned, whether there is one thread or multiple threads should not matter. You simply take entire memory state, and that includes state of all the threads, and you save it. But each socket connection is treated independently. So you will basically send out two marker messages on two of your socket connections. They might end up at the same other destination process. That does not matter. You take all of your open socket connections, just send a marker message. Okay, whether they are going to the same process, other processes, doesn't matter. Because your goal is the socket buffers on every socket connection must be saved. Okay? So where the messages come from is not material. What is more material is OS buffers have to be saved, because those messages will get lost if you don't do it. So that's the way it will work if you have multi-threaded scenario. Okay? So you won't treat threads as independent processes. Threads within the same process still act as a single process as far as checkpointing local state is concerned. Okay? So here's some other questions. So you could ask, will you be guaranteed that if I have an outgoing marker, I will actually, and I start recording incoming socket messages, that I will at some point stop recording, that the marker message is guaranteed. Okay, will this algorithm actually terminate, or will there be some weird scenario where there is some loop and I never get a marker message and I keep recording forever? Is that clear what I asked?
Since we are waiting for all the neighbors to send back the marker message, if one of the peers has like disconnected from the network, so we will always be holding back for that peer to send the message.
Okay. So the point being made is, if one of these processes actually dies or departs, then the algorithm will not terminate. That is true. Okay. So we will assume for now that the processes are stable. While the checkpoint algorithm runs, you don't have failures or disconnects. If some processes fail in the middle of the checkpoint, then all bets are off. Okay, then that is given. But let's assume there are no failures or departure. If the number of processes is static, I am simply asking, if you basically send an outgoing marker and start recording your incoming messages, are you guaranteed at some point a marker message will come back and you don't actually need to, that you will actually stop recording? Okay. And you can ensure, just analyze this scenario as between any two pairs of processes that have an active socket connection. Okay. And I already said that if you have regardless of what else is happening, if you just take two processes, okay, and just take a socket connection, you will see that my outgoing connection is your incoming connection, and vice versa. So if I send a socket, if I send a marker message here, okay, it is guaranteed that when this marker message reaches there, another marker message will be sent, because you always send it out on your outgoing connection. So if you send something here, something is guaranteed to come back. And when you receive a marker message on your incoming channel, that says stop recording. Okay? So you are guaranteed to receive a stop recording message on your incoming socket. Okay? Yes.
Is there some sort of indication that pairs those? What happens if A and C both decide to start a snapshot within the time frame between when one starts but the other hasn't yet received its message, its marker?
So that's a good question. The question is, since I said any process can initiate a snapshot, the question is, what if A and C initiate the snapshot at more or less the same time? Okay? So you can actually have multiple snapshots in progress, but then you have to distinguish between marker messages for a particular snapshot. Okay? So in that case, what you have to do is you will say, let's say every snapshot has a unique ID. Okay? So then you will basically attach with a marker a snapshot ID. So if you receive multiple marker messages for two different snapshots, you just treat them independently. So you just end up with two saved states for two different checkpoints that are completely independent from one another. So you don't confuse marker messages. So you mark the marker message with a snapshot ID. It will get around the problem of concurrent snapshots that were started by independent processes. Okay, so that's a simple thing to actually deal with.
Why can't you have only one process? It's like master.
Yeah. So you could typically what you want. So question is, why can't you use a one process which is tasked with initiating a snapshot? That is what you would normally do. Okay, but the algorithm doesn't depend on that. You can have any process started, not just a master process. So long as you attach your snapshot ID, you don't get confused by what does this marker message mean? What snapshot is it associated? That's all you're saying. Okay, but ideally you would want to do what you said and not even have this problem. But it can be dealt with. Yes.
The notion of sockets, right? Like you're basically dealing with sockets and waiting for the markers on each socket level. So even if a client dies or disconnects, so that socket is basically that there's no listening happening there. So it will not go into infinite wait for a marker. Right?
Okay, so the question is, if some process dies, the socket connection is broken down, and you won't be recording infinity. All I was saying, I wasn't saying the algorithm will not terminate if some process dies. All I was saying is you will basically not get the full state of your system if some process dies. Right? If some process dies in the middle of taking a checkpoint, maybe it died before you say the state was saved to disk. Maybe it basically sent outgoing marker on two of its three socket connection, then it died. Okay? So you could have all sorts of bad cases. So in that case, the checkpoint will not actually be the right one you can restart. It might even terminate, but it still should not be treated as a correct checkpoint because the process is dying means something could not have been saved that must have been saved. That's all. Okay? Yes.
Do the markers propagate so that they would keep the same sequence number, or when the next node receives a marker, does it only respond with that sequence back to the originator and start a separate sequence going to its other neighbors?
Right. So question is, do markers have hop counts that are associated with it, and do they get incremented and so on? That's basically another way of asking that question. I'm going to just draw a simple topology where there are A, B, and C, and every process has a connection to every other process. Okay, so in this case, if A starts a snapshot, it saves A, it sends marker messages on outgoing channels, and it starts recording its incoming channels. Okay? Now, your outgoing message is going to B and C. Okay? So when this marker is received at B, it could take a snapshot and send an outgoing message to C. And now, depending on the network speed, either A's marker will be received here first or B's marker will be received here first. It does not matter in what order you receive it. You don't have to deal with hop count. When the first marker you receive for any snapshot is the one that says save your state. Okay? And then you just wait for all of, and then you start recording your incoming channels, and then you just stop recording when the marker is received. So you might have these weird cases where multiple markers are received before you have even taken a checkpoint, and you just take the first one, you save it, and then you start recording. And you don't have to increment your hop count or anything like that. You just need to have either only one snapshot in progress, okay, by just having a master initiated, or if you have the possibility of multiple ones, attach a unique snapshot ID, so marker messages can be distinguished. So you just treat them as independent snapshots and just take the first marker for every snapshot and then save your state. That's the way you will distinguish between them. Okay? So let's just stop here, we ran out of time. So as I had said at the beginning of the class, I will give an homework out, which is going to be a practice test, which is essentially last year's midterm. I'm going to give us your homework. You do not have to turn it in. Okay, it's not a graded homework. Okay, I'll hand that out today, so you all have spring break. You should use to study for the course for spring break. Lab 2 will also come out this week. But it will do well after the midterm. Okay, so if you want to prioritize and study for the test, feel free. If you want to get an early start on the lab, feel free as well. So I'm just handing it out a bit earlier than usual, so you can decide how you want to spend your spring break. Okay, so the two things are coming out today, which is lab 2 and homework 3, okay, which is a practice exam. Right, so with that, let's stop.